In this video, we'll look at the other asymptotic notations. So you've already seen big O notation, which was used as an asymptotic upper bound. Correspondingly, we also have big omega notation, which defines an asymptotic lower bound. So big omega is also a set of functions defined as follows. So we have that big omega g of n is the set of functions f of n, so that there exists some positive constant c here, which we'll multiply by g of n, and some starting point, n sub 0, so that for every value of n beginning at n sub 0 and moving forward, we satisfy the inequality that c times g of n is less than or equal to f of n. Now, let's see how this relates to big O notation, which you saw in the previous video. Big O notation was an upper bound. So because of how we've now defined big omega, then if we have a function, let's say f, which is big O of g. So if f is big O of g, then that means that g is big omega of f. So this is kind of how big O and big omega relate. And we could say the other way. Okay? So intuitively, big omega is the set of functions whose rate of growth is the same as or higher than g of n, which makes g of n an asymptotic lower bound for f of n. And this is like saying, although not exactly, but you can sort of think of it this way, that with big omega notation, that if f of n is big omega of g of n, so f of n is big omega of g of n, that in that case, this is kind of like saying that f of n is greater than or equal to g of n. So you can sort of think of this as greater than or equal to. G of n is our asymptotic lower bound. Now we also have big theta notation. This essentially combines big O and big omega, so we could equivalently define this as, rather than the definition we have here, we could equivalently say that big theta of g of n is equal to the set of all functions f of n. Let me just put f here. The set of all functions f such that f is big O of g of n and f is big omega of g. So this is an equivalent definition. We're saying that in this case, f is big theta of g of n if g of n is both an upper bound and a lower bound for f of n. So this makes g of n an asymptotically tight bound for f of n. This is essentially the set of functions with the same rate of growth as g of n. So you could think of this, again, not exactly, but you could think of this as like saying that f of n is equal to g of n. This is to compare with our less than or equal to with big O, greater than or equal to with big omega, and now equal to with big theta. So we can see how they relate with these pictures. On the left, what you have here, everything in yellow is the set big O g of n. So g of n is our asymptotic upper bound. So we have, you can again think of this as saying f of n is less than or equal to g of n. This is kind of like saying that asymptotically. In the middle, we have that everything in yellow is the set big omega g of n. Here, g of n is our asymptotic lower bound. So this is like saying f of n is greater than or equal to g of n. And what you just saw was what we have on the right. Everything in yellow is the set big theta g of n, where g of n serves as both an upper and a lower bound. So Again, you can think of this as like saying f of n is equal to g of n. Again, not exactly, but you can kind of relate them in this way. So when we think of it this way, we have two missing relatives here. Strict inequality, strictly less than or strictly greater than. And this is where little o and little omega come into play. So little o is more strict than big O notation. So if f of n is little o of g of n, then it's also big O of g of n. But if f of n is big O of g of n, that doesn't necessarily mean that it's little o of g of n. So remember the big O definition. Let me put it in over here in red. So the big O definition is there exists some positive constant c, and basically everything what you have remaining here is the same as what's below. There exists some positive constant c, and there exists some starting point n sub 0, so that f of n is less than or equal to c of g of n. That's the big O notation. Little o notation, this is the only place where it differs. So we have the same requirements, everything on the right here, but what makes little o more strict than big O is the fact that we require for this condition to be true, not just for some starting point c, for some positive constant c, but for all of them. And the same thing for little omega. If we compare this to big omega, then again, our definition for big omega was that there exists some positive constant c, so c greater than 0, and there exists some starting point n sub 0, so that c times g of n is less than or equal to f of n for every value of n beginning at n sub 0 and moving forward. So that was our definition of big omega. Little omega is the same, this last part is the same, except we're saying that this condition must hold for all constants c greater than 0. So again, little omega is more strict than big omega. So if we have that f is little omega of g, then that also means it's big omega of g. But if f is big omega of g, it doesn't go back. It doesn't mean that it's little omega of g. So again, what's making this more strict is that we are requiring that this condition holds for all constants. Okay, so we have covered big O, big omega, and big theta. Again, this is kind of like asymptotically saying that f of n is less than or equal to, greater than or equal to g of n. And when we looked at little o, this is now giving us kind of equivalently those strict inequalities, asymptotically speaking. So we won't use little o and little omega notation that much. It's mainly used when precision is essential, but we will use big O and big omega and big theta quite frequently. These will be plenty sufficient for our purposes. Now, I just want to end with, we're finished with the analysis of algorithms part of this module, but there are a few basic math principles I'm working with the assumption that you know already because of the prerequisites of this class. But if it's been too long for you since you took Calc 2 or discrete math, then you may want to refresh on some of these ideas. For example, we will use summations quite a bit, especially when counting primitive operations to determine the runtime. So it will help you to remember, for example, that the sum of the first n integers, so 1 plus 2 plus 3 plus 4 all the way up until n, is equal to n times n plus 1 all over 2. So we're going to encounter that quite a bit. Logarithms and exponents will also be used extremely often. So remember that log base b of a is equal to c, only if we have to take b to the power of c in order to make it equal to a. So for example, if we have, let me erase the, let me write it down here. So if we have log base 2 of 8, the result of this is what power do we have to take 2 to the power of what equals 8, and that's 3. Okay. Or as another example, let's say we had log base 3 of 9. What is this equal to? This is asking what power do we have to take 3 to in order to make it equal 9, and 3 to the second power, 3 squared is 9, so the answer to this is 2. Or that's an L, log base 3 of 27. What power do we take 3 to in order to make it equal to 27? This is 3. Or let me just do a couple more to make sure you remember this. Log base 2 of 16. If we take 16 to the power of 4, we get, excuse me, if we take 2 to the power of 4, we get 16, so this is equal to 4. And one more, log base 3 of 1. What do we have to take 3 to the power of in order to make it equal to 1? And this is 0. So unless otherwise stated, if there's no base given, you can assume that we're always working with log base 2. Let's see here. Basic probability. Actually, before I get there, let me just kind of remind that we're going to work with logarithms and exponents a lot. So this is the definition of a logarithm, but we have a few other properties for them that we'll see, like how to handle if we're taking the logarithm of a product, or you know, how would we express this if we had log of x over y? And we're going to use these quite a bit. So just kind of make sure that you're familiar with these, and if you need to, write them down and just keep them in your notebook paper so that you can reference it later. Okay, so for basic probability, again, you can check these parts of the section of your book to refresh. But for example, one of the things you'll want to remember, what we'll see that, you know, if you flip, let's say, a fair coin 10 times, how many times would you expect it to be tails? So that would be half the time, 5 times. Right? And then lastly, I want to talk about proof techniques. So we will prove things in this class often. So make sure you are familiar with the basic proof techniques. So if you have a statement of the form P implies Q, so if P then Q, and you want to prove that this is true, there's a few ways you could go about it. You could use a direct proof. With a direct proof, you would show that this implication is true by first assuming that P is true, and then use that to show that Q is also true. Or you could use an indirect proof. So you could show that the contrapositive is true, which means that not Q implies not P. So this is a proof by contraposition. So we assume that Q is false, and then use that information to show that P is also false. So that's a proof by, let me write that out here, proof by contraposition. So we take the contrapositive and then we prove that directly. So this is an equivalent way to prove that P implies Q. Or you could also use another indirect technique, which is a proof by contradiction. Let me just put it that way, contradiction. So in order to, again, prove that P implies Q, we start off by assuming that that statement is false, and then reach some kind of a contradiction like an even number is an odd number, which means that we were wrong to assume that this implication was false to begin with. So to prove by contradiction this statement, we would say, assume that Q is false and P is true, and then reach some kind of a contradiction. You should also be familiar with both mathematical and structural induction. Oops, okay. So this is usually if we want to prove that something is true for all integers. With a mathematical induction, we would start by showing that this is true for some starting integer, and then show by induction that if this is true for some integer k, so this is our property P, if it's true for some integer k, then it's also true for the next integer k plus 1. And between those two things, the base step of showing that this property is true for some starting point and also that if it's true for some point, it's true for the next point. This is what makes up a proof by mathematical induction. We'll also see proofs by structural induction too. And I'm going to hold off on reviewing that one because we're actually going to see an example of it in the next topic, elementary data structures. So if any of these are not familiar to you, or it's been too long since you've had to do that, please review the appropriate sections of just the first chapter of our book to make sure that you're working from a good starting point. Okay, if you have any questions, again, post on Piazza, let me know, and I'll see you in the next video.